Hi everyone. So today I'm going to start with talking about more about implications. So remember, implication or the imply symbol is this, or otherwise written as that. So if I have P, Q, so these are the same thing. So this one reads as P implies Q, and this one also reads as P implies Q. It just may look a little strange because in English we read from left to right. But yeah, okay. So that's what I mean when I'm talking about, we're going to talk about implications. The converse of P implies Q is Q implies P. So this is only for implications. So this is not like negation where you could negate any statement that you want. This, talking about the converse of a statement, it's already assumed that the statement you're talking about is an implication. So how one of my professors at my undergrad always explained this was, like those Converse shoes. I don't know if it's spelled the same, but that's kind of how you think about it. Like you just flip flop them. Shoes make you move places. Yeah, I don't know. So that's just a quick definition. Now let's think about what needs to be true for P implies Q to be a false statement. So if we're thinking about this, maybe let's draw up our truth table, okay, and look at that. So we want P, we want Q, and then we also want P implies Q. So P, we just go true, true, false, false. So P implies Q. If P is true and Q is true, it's true. Well, whenever P is false, P implies Q is going to be true. So the only time that it's false is when P is true and Q is false. Okay, so I'm going to spend some time on this because this is extremely, extremely important. Okay, and I really want you to, I need you to leave this class knowing this, okay? All right. So we would need P to be true and Q to be false. Okay, so it's not one or the other, because if P's true, well, if Q's true, then it is true. Okay, but if Q's false, well, if P's false, then it's okay, right? So we need it to be that P is true and Q is false. Okay. Another way to say that Q is false is to say that the negation of Q is true. Okay. Therefore, the negation of P implies Q is logically equivalent to P and not Q. So I hope that's kind of clicking. If not, look over it again or let it marinate, look at it tomorrow. But this is very important, that the negation of an implication is an and statement. It's the if part and negation of the then part. Okay. Fabulous. So what if we want to think about the negation of an if and only if statement? Well, nothing really comes to mind immediately, because we haven't really talked about this back and forth arrow very much. I remember in one of our videos we did talk about the statements on either side of an if and only if have to agree on truth value. So either if the if and only if statement is true, okay, then on either side they both have to be true or they both have to be false. Either one of those, when they agree, give that the if and only if statement is true. Okay, so let's do a quick reminder and let's look at our table. So if we said P if and only if Q, when is this true? Well, it's only going to be true when P and Q agree, which is the first and the last. Okay, so this is interesting so far. Something that you may have noticed is the notation here kind of lends itself to this, but the arrows on both sides. So what if we looked at, and if you remember how I was talking about it before, it does have kind of this back and forth between Q and P. Let's look at what Q implies P looks like. Okay, so first we have true, right? Okay, but anytime that Q is false, it's going to be true. Okay, so the only time it's false is when Q is true and P is false. That lines up with everything that we've said. Excellent. So if I look at these combinations, so how about I'll highlight in pink whenever P if and only if Q is true, and I'll highlight in blue every time P if and only if Q is false. So what do these have in common? So you might notice, well, this one's false, but this one's true. And then in the middle we have false. Similarly, this one's true, this one's false, and then in the middle we have false. But every time either side has a true, the middle has a true. And I'm definitely leading you. I don't expect people to see this right away. From what we know about truth tables, the middle column looks like an and statement of the other two columns. What ends up being true is that P, if and only if Q, is equivalent to if P then Q, and if Q then P, okay? Because what do we get? So both of them have to be true. Well, that only happens at the top and at the bottom. In the middle we have false. Okay, so then yes, they are logically equivalent. Okay, so if these are logically equivalent, then the negations of them, of each, will be logically equivalent. Okay, so the negation of this one will equal the negation of this one. And the negation of this one, combining all the information that we have so far, we should be able to figure that out. Okay, so I would suggest pause the video to see if you can do it. Okay, so if we remember back to a previous video, I did say that the negation of statement and statement is going to be the negation of the first statement. So negation of P implies Q. And what I mean by same as is logically equivalent. I just don't want to have to keep writing that. Maybe I'll write like LE for shorthand. Okay. I just made a mistake. Hope you saw that. So it's not and, we're going to flip it to or, okay? Anytime we negate an or an and statement, we flip it and we negate both sides. Okay? All right. Fabulous. So now we just learned today what the negation of an implication is. So we have P and not Q, or Q and not P. Ooh, okay, so this is the negation of if and only if. P if and only if Q. Fascinating. Okay, Danica, that's all fine and dandy. Now we know a little bit more about if and only if. How would we prove an if and only if? Okay, so here I have an example for us. When A is an integer, then we have the statement A is odd if and only if A squared is odd. Okay? So if I want to prove that this is true, I could also prove both directions have to be true. Okay? Because remember, P if and only if Q is logically equivalent to if P then Q and if Q then P. Okay? So what I'm going to do is it's kind of like showing that two sets are equal. I show subset one direction, I show subset the other direction. So this one's going to be kind of similar to that in that it's a two-parter that combine to make one statement. Okay? So I'm going to show that if A is odd, then A squared is odd. And then I'm going to show after that, if a squared is odd, then a is odd. Okay? All right, so let's start our proof. So first I want to say that a has to be in the integers. So let a be in the integers. And maybe you're thinking to yourself, well, can't the reader just read the question themselves? You just want to be extra clear, okay? Your proof should be a standalone object. All right, so let a be an integer. So just like with the subsets, just to keep track of what I'm doing when, I'm going to write in the parentheses like which direction I'm going. So what I mean by this is, I'm going to come from a is odd. I'm going to say if a is odd, then a squared is odd. So that's what I'm trying to prove right now at this point. Okay? So remember the if-then statements or the implication statements. If a is even, then that implication statement's true. I don't even care if a squared is even or odd. Okay? So who I really care about is when a is odd. Okay? Because if a is even, done. Check. Okay, so the interesting stuff is when a is odd. So I'm going to assume that a is odd. Then by definition of being odd, there exists some k in the integers, so you could pick a different variable, that's fine, such that a equals 2k plus 1. Okay, so that's just the definition of a being odd. So let's talk about what it is that we want. So, sorry, I forgot to say this. Whenever I start a proof, I like to start with definitions and just talking about what that definition means, because then I'm laying out all my tools that I can use. It's like, let's say you know how to fix cars or something, and you go over to someone's place and you're going to fix their car. Instead of keeping all your tools in the car and then going back and looking for it, grabbing it, bring it back, you want to be able to keep it and nicely organized, and then you show up and you lay it out. Okay? And then you think to yourself, okay, now I have all my tools in front of me. How the heck am I going to use them? Okay, so that's when you start talking about what you want. So I want to find some element L in the integers such that a squared equals 2L plus 1. Right, because then that would mean that a squared is odd. Okay, I don't really know who L is yet. Hopefully somewhere down the road I'll be able to find some integer that satisfies this. Okay, so I have a up here. Well, I know how to square a. Why don't I just try doing that? And remember, you can always ask your reader to consider something, okay? So I did teach before that you want to explain how you get from one line to the next, right? So you might be thinking, well, if I don't talk about what I want, that might be kind of a jump for the reader for me all of a sudden to just start talking about a squared. But that's okay. You're not assuming anything about a squared. You're just saying, here I have a. Well, I can multiply a by itself and get a squared. Okay. So that's going to look like this. Let me talk about what that equals. 1. Okay. All right. So I want this statement, this formula to look a little bit more like this. So I want 2 times an integer plus 1. Okay, well, why don't I start by singling out this plus 1, okay? I'm not going to touch that plus 1. I want that to stay on the end. Now, the next question I'm going to ask is, can I factor a 2 out of this? Well, I most certainly can. Awesome. So let's do it. So we have 2 times 2k squared plus 2k, and then after that, we have plus 1. Okay, awesome. So now here's where we use some of those facts that I gave you a few weeks ago. I can't remember how many weeks ago. That integers, when you multiply 2 integers together, you get an integer. When you add integers together, you get an integer. Things like that. So now all I have to say here to show that this could be my L is I need to say that it is an integer. So since k is an integer, then 2k squared plus 2k is an integer. So you can put in parentheses if you're a little worried that someone's going to misinterpret it. Right, so I don't need to talk about how 2 is an integer, and I also don't need you to talk about like that multiplication of integers is an integer or addition of integers is an integer, but I need you to understand that that is important here, okay? Because we're not talking about division. Talking about division in the integers is a big no-no, like just dividing stuff randomly. If you talk about someone being a divisor of someone else, awesome. But we can't just start dividing numbers, okay? Because we don't know that we're going to end up back in the integers. And we just want to stay in the integers, okay? A squared equals 2L plus 1 for some L in the integers. So A squared odd. Okay, so do you see that, how I'm kind of letting 2k squared plus 2k equal L here? So let's start doing the other direction. So now I'm going to draw it this way. And what I like about writing it like this is if we scroll up again, I know that I'm going to start with a squared is odd and then show that a must be odd. Okay? All right. Assume a squared odd. Then there exists. So now I'm in a totally different part of my proof. I could use k again if I wanted to, right? So everybody knows, especially when you write that like parentheses and stuff, hey, I'm talking about something different now, okay? There exists, let's say, n in the integers such that a squared equals 2n plus 1. Fabulous. So that's what I did last time, right? I just started unraveling my tools. I was talking about what it means to be odd. Well, what can we really say about a? Not every integer is a square, so if we do square root this, 2k plus 1 square rooted, yeah, it gets ugly fast, okay? So instead of this, let's go back to, so you'll find that this is a theme in the class, is we go back to some true dichotomies. So remember, dichotomy means one or the other is true, not both, not neither. Okay? So for example, if I flip a coin, it's either going to land heads or tails, right? So since a is an integer, we have a very nice dichotomy about a. A is either even or a is odd. Okay? So we have two cases. So our first case is a is even, and our second case is a is odd. Okay? So part one. So we're assuming that a is even. So then there exists an m in the integers such that a equals 2m. All right, let's kind of follow how we did the first part of the proof. Then a squared equals 2m squared equals 4m squared. But that equals 2 times 2m squared. Since m is in the integers, then a squared is even. Okay, and this really in the course, maybe I should say then 2m squared is in the integers, so a squared is even. Okay? Eventually you'll be able to cut out that middleman. I mean, I still want you to be talking about that, but wait a minute. We assumed that a squared was odd. But we assumed a squared is odd. Therefore, since a squared can't be even and odd, then a can't be even. Okay? All right, so that's part one. Now part two, if A is odd. But if you notice, we already did that in the first part. And if you didn't notice that, that's okay. You would just do the same thing as above. Okay, so part two, if A odd, then consider first part of proof. All right. Okay, so I left out a bitty part. So I want a short conclusion up here. Okay, I'll write it in a different color, so hopefully it stands out. Therefore, if A odd, then A squared. Okay? So that just means that A odd implies A squared odd. Now down here, I'm going to write from 1 and 2. If A squared is odd, then A must be odd. Therefore, A odd if and only if A squared odd. Excellent.